Here are the worked out solutions to the Chapter 5 test. We're going to start with graphing. You'll have one of these on your final exam. It'll either be exponential or logarithmic. So when you're graphing these, the first thing you need to pick out is your base. Right here, and on number 2, the base is 3. So think of the parent function as being 2 to the x, and I'm going to make a base table, so x's and y's. If I plug in 0, 2 to the 0 is 1, and if I plug in 1, 2 to the 1 is 2. That's my base function. And then we're going to apply a transformation. -6 and then the -5 here. I'm going to go right 6 and down 5. So I'm going to move my x's to the right 6 and my y's down 5. And those are the points you're going to plot here. And the asymptote is always this last number, whatever the up and down movement is, because the original asymptote is at 0, and I moved everything down 5, so that also moves the asymptote down 5. So that's going to be y equals 0, not 0. It is going to be y equals -5. So I'm going to plot that first. 1, 2, 3, 4, 5. And I draw a dotted line here for the asymptote. And I'm going to plot the new function, 6, -4. 1, 2, 3, 4. And 7, -3. And it is exponential growth because the base is bigger than 1. The domain goes left to right, so this domain is -infinity to infinity, and the range is from parentheses -5 to infinity. Logarithmic graphing is a little bit more challenging because a logarithm is an inverse of exponential. So for 3 to the x, since the base is 3, you would have 0, 1, and then 3 to the 0 is 1, 3 to the 1 is 3. But you will do the inverse of that. So log base 3 of x then is 1, 3, 0, 1. So you have to switch the x and the y. Then you can do your transformation. You go to the right 3 and up 1. So I'm going to move my x's to the right 3, so I'm at 4, 6. And my y's up 1, so I'm at 1, 2. With 3 to the x, our asymptote would have been y equals 0. So for log base 3 of x, then it's going to be x equals 0. It changes to a vertical asymptote. But then I moved, when it's a vertical line, you would want to move it to the right 3. So I'm going to move my vertical asymptote to the right 3. And then I can plot my points, 4, 1, and 6, 2. And these are like sideways exponential graphs. So my asymptote is x equals 3. My domain goes from 3 to infinity, and my range is -infinity to infinity. Now we're going to do some expanding. The basic rules for expanding are if you are multiplying, then that changes to addition. If you are dividing, then that turns into subtraction. And then if you have an exponent, the exponent goes out front. So we're going to combine these all into one problem. So first thing I want to do is deal with this 4 outside the parentheses. That goes to both exponents. So I can rewrite this as log base 5 of m to the 8th n to the 12th. Then this is multiplying, so I can separate that. Log base 5 of m to the 8th plus log base 5 of n to the 12th. I can bring exponents out front. 8 log base 5 of m plus 12 log base 5 of n. And that is the fully expanded form. On number 5, we want to rewrite a radical as a fraction exponent. So If you've got a root and a power, you can rewrite that as power over root. So I'm going to rewrite this. I've got log base 2 of x to the 12 over 3 times y to the 1 over 3. And 12 over 3 simplifies. Log base 2 x to the 4th times y to the 1/3. Multiplication splits up to be addition. Log base 2 x to the 4th plus log base 2 y to the 1/3, and then exponents go out front. 4 log base 2 of x plus 1/3 log base 2 of y. And you can go backwards to condense. So just like I separated them, I did the multiplying separating to addition, and then I moved the exponents when I was expanding. To condense, I'm going to deal with the exponents and then the adding and subtracting, condensing that. So first I'm going to move this exponent up right here. So it'll be log 64 to the 1/3 plus log x plus 5. And 64 to the 1/3 is like the cubed root of 64. So really it's just log of 4 plus log of x plus 5. Addition turns into multiplication, so I can write the word log one time, and then I have 4 times x plus 5. You can leave it like this, or you can distribute the 4. Log of 4x plus 20. So either answer is correct. I'm going to do the same strategy with number 7. I'm going to bring my exponents up top. Neither of these work out nicely, so I'm just going to leave them like that. And then subtraction turns into division when I condense. So natural log of 3 to the 7th over 8 to the 1/2. And I'm okay with leaving it like that. Since we're looking at a log and a natural log here, I wanted to talk about the difference. You'll notice neither of these have a base written. So when you have a log of anything, it has an understood base of 10. So log of a equals x, for example, I would have an understood base of 10. If there's no base written there, you understand it's 10. And if I wanted to convert that to exponent form, it would be 10 to the x power equals a. Natural log has its own understood base. That has a base of e. So then I could rewrite it in exponent form as e to the x equals a. And both of these properties right here will help us solve logarithmic equations and exponential equations like we're going to do on the next page. When you're solving with logarithmic equations or exponential equations, you want to condense first, and then if it's log equals number, you'll convert it to exponential form. So right here, I've got a plus sign, so I can condense that to a single log. Addition turns into multiplication. And I'm going to distribute the x. Now that I have it condensed, I'm going to set it to exponential form. So this has an understood base of 1. So it's 10 to the 1 equals x squared minus 3x. This becomes a quadratic equation, so we need to get everything to one side. X squared minus 3x minus 10 equals 0, and we can factor. What multiplies to get negative 10 adds to get negative 3, and that is going to be negative 5 times 2. So this factors to x minus 5, x plus 2 equals 0. So x equals 5, x equals negative 2, and we need to check our solutions because you can never take the log of a negative number. So if I were to plug in negative 2 into my original equation, I get log of negative 2, which can't happen. So negative 2 is not one of your answers, and 5 is the only answer. In number 10, I have a log equals log equation. So I am going to condense, and then if it's log equals log, I can drop the log part and set the components equal to each other. So first I'm going to condense this. It's addition. So I can condense this to say log base 5 of x times x plus 1 equals log base 5 of 20. And we can distribute the x right here. Log base 5 of x squared plus x equals log base 5 of 20. Since they both have a base of 5, I can drop the logs and set their components equal to each other. Again, we have a quadratic equation, so I'm going to get everything to one side so I can factor. And now I want to know what multiplies to get negative 2, adds to get 1, and that would be 2 times negative 1. And so this factors to x plus 2, x minus 1. Then x equals negative 2, x equals 1. And we want to check our solutions again. If I plug in negative 2 into the original equation, I'm taking the log of a negative number, so that's not one of our answers. X equals 1 is the only answer. Number 11 is already condensed and simplified, so it's in exponential form, so I'm going to convert it to logarithmic form. E is the base, and whenever E is the base, we're going to use natural log. So it's natural log of the other side equals the exponent. And we can type in natural log of 16 in our calculator, and we'll just round it to a few decimal places. Natural log of 16 comes out to 2.773 equals 3 minus 5x. Then I'm going to subtract 3 from both sides. So I have negative 0.227 equals negative 5x. And then I can divide by negative 5. So then I'm left with x equals 0.045. And that is your answer. We're going to skip number 12. That requires a whole lot of work. I actually think that was a typo. It should have been multiplying right there. Number 13, we've got exponent equals exponent. So I can drop the bases here and set their exponents equal to each other. And that is also quadratic, so I'm going to get everything to one side. And we can factor. What multiplies to get 3 adds to get negative 4. Negative 1 times negative 3. So I have x minus 1, x minus 3 equals 0. X equals 1, x equals 3. You can raise any base to any exponent. There's no restrictions there. So these are both the answer. This next one, we are going to condense and get the log by itself. So I can subtract 6 from both sides, and I can also move this 4 up into the exponent. So I have natural log w to the 4th equals 6. This has a base of e, so I can rewrite this as e to the 6th equals w to the 4th. And I can take the 4th root to get rid of the 4. So now I have the 4th root of e to the 6th, and I can actually rewrite that to e to the 6 over 4, because that'll make it easier to type in the calculator. So above the natural log number, I'm going to write e to the 6 divided by 4, and I'm left with 4.48 as my answer. That's one way to do it. The other way to do it would be to divide by 4, like isolate the natural log w from the very beginning. So let's do it that way too, and you'll see how you get the same answer. 4 natural log w equals 6. I divided or subtracted the 6. Now we can divide by 4. Natural log of w equals 6 over 4, or 3 over 2. This has a base of e, so I'm going to do e to the 3 over 2 equals w, and you're typing the exact same thing into the calculator, and you'll get 4.48. Let's look at number 16. I've got log 10 to the x plus 4 equals 12, and when there's no base written here, you can understand that there's a base of 10. And so if you didn't know the specific property that log base 10 of 10 equals 1, then you could convert it to exponential form. And since they have the same base, you can drop the base. Didn't mean to do highlighter there. And you're left with 12 equals x plus 4. X equals 8. And that's all there is to it.